Feigel'man started this lecture course that will go on for a few weeks. It's always going to be on Wednesday. This Wednesday, the next one is in 2 weeks, right? And then 3 Wednesdays in June. The course is about spin glasses, and it's really an opportunity to learn something about the subject that is partially dealt with in CISA in the course of Scardicchio, but not at the same depth and level what Misha is going to tell us. So he's going to cover the entire spectrum of glasses, including Parisi solution, dynamics, quantum glasses, and all sorts of things. So I think it's comprehensive, and thanks a lot for agreeing to give us this lecture.
Well, I'm not sure I will just everything about glasses. That is difficult to do in 10 lectures. But definitely it will be a very subject course with quite some emphasis on very old results which were obtained by Leo Youngman himself in 80s, and which are definitely forgotten, but it's a pity that they're forgotten. So I will tell you something about it. Now, usually I assume that useful lecture course is consists not only from lectures themselves, but also from some activity of students afterwards. In any case, if anyone is interested to have a contact with me, just send me an email. To this address. Lecture materials will be corrected on the website of our program. And I just will distribute the link to everyone who will write to me, so I will know whom to send. Also, Dmitry is doing recording. So let me start, and the first lecture is of very introductory kind. It is just description of major physical phenomena in real glasses, spin glasses, and so on. The story of spin glasses started from experiments on some rather specific kind of materials which are magnetic alloys like copper manganese or gold ferro. This proportion of magnetic atoms is very small, as written here is X. So you have a normal metal like copper or gold, and small concentration of magnetic atoms, which has a localized speed. Interaction between these magnetic moments is due to intermediate media of normal electrons with a Fermi surface, with Fermi wave vector, and so on. So this is what is called Ruderman-Kittel exchange interaction. And this interaction is basically shown here. Its main feature is that it decreases as a third power of distance between magnetic moments, but it oscillates very fast. It oscillates on atomic scale, because this here is the Fermi wave vector of a matter. So it means that if you consider one spin here, another spin here, at a distance r, you don't know what is the sign of interaction, because you can change this r by a small amount, like atomic lattice spacing, and due to this oscillation factor, the sign will change. And this is the whole story that if you will try to find some low energy state of such a system of spins, you don't know what it is. It is not ferromagnet. It is not anti-ferromagnet. Because there is no evident preferred structure in the direction of these magnetic moments. Another example, different example of random interaction which leads also to classic behavior is a usual dipole interaction. You may have either magnetic dipoles or electric dipoles. I will show later more details. In any case, interaction is like this. And if you, here we don't have such a fast oscillations like in a previous example, but still average of this interaction over three-dimensional sphere is zero. So again, there is a problem, what is the most low energy state? There are many different classes of classes, example of classes, which many of them I will be talking about. But let me first formulate what are the major ingredients of classic behavior. First of all, it is presence of frustration. Frustration means you have in the system interactions which compete between themselves. And the simplest example is consider triangle with Ising spins and with anti-ferromagnetic interaction. So here will be anti-ferromagnetic. This pair is in a good low energy state. This one also in a good state, but this third one is in a bad state. You can flip any of these spins, but still you will always have some part of interaction which are in the high energy state. This is a phenomenon of frustration in the simplest form. Now, second ingredient, which is usually present, although there are some counterexamples, but usually it is present. It isn't disorder. So the system is doesn't have translation in rate. And third, again, it is not necessary, but it will be so in a major part of our discussion, is that for some this or that reason we can consider our major variables like spins to be just classical variables. So of course in physics they are all originally quantum, but in many cases these quantum fluctuations can be neglected and then we can deal with classical objects. But I hope to discuss quantums and glass as well when it comes later. at more details, examples of major main options. Metallic spin glasses, which I already mentioned. Apart from third three examples, with the matrix of copper, gold, or silver, sometimes we may consider a little bit different kind of metallic spin glasses with yttrium gadolinium. Gadolinium has a magnetic moment, yttrium is just a matrix. But interesting story is that this yttrium is close to spin density wavelength stability. So it is not just simple normal metal, but something which has already specific, say, spectrum of magnons in this yttrium. It has some kind of structure which, with a minimum of energy, rather close to zero. And it is almost spin density wave. And when you put some magnetic moments, it becomes a spin density wave, but you put these moments at random positions. So again, it is a frustrating system. Now, second class, dielectric spin glasses. Many different compositions of dielectrics with the European X, European is magnetic, or this last material there, chromium is magnetic. Here there is no conduction, no permeable vector, but just interaction is between nearest neighbors and next nearest neighbors, and they are opposite sides. So frustration. Next class, dipole glasses, iomagnetic, like this first lithium, chromium, yttrium, ferro, very popular materials, which their spins can be considered as just Ising spins directed along some axis, up or down, and the interaction between is purely dipoles. And also a completely different material like shown here, electric dipole glasses. Here you have electric moments instead of magnetic moments. Second class of glasses, what I call here electron glasses. This is electronic materials which are in an insulating phase, and with a relatively large concentration of electrons, shown here, like 10 to 18 to 19, with a very high degree of disorder which is experienced by these electrons. So electrons are localized, but they also interact. There are two most popular examples of this kind of systems: amorphous indium oxide and granular aluminum. This is very funny system and very popular now due to some possible applications in the superconducting. You may have granular aluminum superconducting, but you also may have it insulating if you make a tunneling between grains to make it too weak. So it's really some grains, isolated collection of grains of small size with tunneling between these grains. Again here, electrons are charged, they are localized inside grains, and you have a competitive interaction. By the way, if anyone has a question along my talk, just please ask question immediately. superconducting glasses. What is this? Maybe you know that many years ago, Benders and Müller discovered high temperature superconductivity. First samples which have shown these signatures of superconductivity at 40 Kelvin and then on another material 90 Kelvin. First, these materials were fabricated in the form of ceramics. It means very small pieces of this complicated material coupled together again by some tunneling. So, grain here, grain here. Material itself is superconducting. Barefoot magnetic field. Each superconducting photoparameter in a grain is characterized by its phase. And here phase by J. Coupling energy between these two is sum J by J cosine phi r minus phi j. Good. J is positive, so the lowest energy state is the state where all phases are the same. It is a microscopic superconducting state. Now let's apply magnetic field. Then you need to add here something proportional to vector potential and magnetic field. And uniform distribution of phases is not a good solution. You immediately come again to a problem of frustration. And if you have any ordered state where phases are more or less frozen, this will be again a glass superconductor, which has the same actually type of photoparameter as XY spin glass. So you have two components. You can describe it by S, X, and XY, or you can define it by a complex number. So symmetries which can be broken, dynamically broken in classes. Major examples are, here is either Z2, Ising spins, or continuous symmetry breaking like O2 equivalent to U1, or finally Heisenberg O3 symmetry. So, now specific examples.
Sorry, Misha, about yttrium gadolinium, you said that there is a spin density wave essentially. So, which means that you will have to open up a gap, right? So what will mediate interaction between spins?
Why? Spin density wave in pure yttrium it is absent. It is close to instability, but not yet there.
Okay.
So what yttrium does is that it produces coupling between localized spins,
Okay.
which are not exactly of Ruderman-Kittel type,
Okay.
but rather something like cosine R. Here it will be exponent of A over some large distance, and here it seems similar
Okay.
to Ruderman-Kittel, but it is different in some sense, which I will probably describe a bit later during this lectures. Important point is that decrease of amplitude as first power of distance is very slow. It is qualitatively different from third power. And even, of course, there is some exponential factor here, but this radius r is long. It is long because matrix is close to instability itself. And so within a rather large volume, you have a long range interaction like this you cover. It changes the type of the stimulus.
Okay. Thank you.
So, freezing. What was the first signature that something really non-trivial happens? On the left, you see magnetization as function of temperature in one of these stained glass materials, ferrum, manganese, titanium, oxygen. You see three different curves of different color corresponding to different trajectories in a space of temperature and magnetic field. More precisely, red dots, well, on the high temperature you have only one curve, blue, and this red is written ZFC, zero field cool. It means the following, that you cool the sample to some temperature, and then you apply big magnetic field and measure magnetism. You see two parts of this curve, increasing magnetization when you cool down, and then decreasing below some temperature. Now, blue data in full. Here you first set some magnetic field, say 5 Tesla, and then you cool down and measure magnetization during this cool. Above about 20 Kelvin, 21 Kelvin, you are on the same curve, but below your data are quite different. You see that there is a slight decrease of magnetization, and then it saturates at a very much above the spread rates. So, what you have, temperature, magnetic field. You choose a point somewhere here, and field cool procedure is that you go like this. A zero field cool procedure, you go like this, and then increase magnetic field. In a system which is in thermal equilibrium, the result should be the same. But here it is not. If you cool below this 21 Kelvin, you see that the results depend on the trajectory on this space. Now, black points. Black points is what is called thermoreminant magnetization. Namely, you cool in some magnetic field and then switch off this field, and look what happens. If you are above 21 Kelvin, you have zero after you switch off field. But below this temperature, there is some remaining magnetization. So first thing is history dependence of the state of material, which starts below some temperature. And evidently it is not ferromagnet, not anti-ferromagnet, but very simplistic. How to describe it?
And
Yes?
the black that looks like the difference between blue and red, that by chance?
No, it is not by chance, it is quite reasonable. It is just what should be expected.
Okay.
Another, maybe one of the first crucial experiments, like Canel and Midas, 72. Here you see susceptibility, low field susceptibility as function of temperature. And you see for different concentrations of magnetic material, here it is not written, but I think it was copper manganese. For several, the lower is the concentration, the lower you find with some specific temperature of the subject. But another interesting thing which we will consider later on is that you see here data for several values of magnetic field, 100, 200, 300 grams. The larger is the field, the more smoothened is the kit. This is a very important piece of information which we will discuss a bit later. So, strong nonlinearity close to the maximum of this susceptibility. Another important feature, this cusp in susceptibility is also, it depends not only on the magnitude of field, but also on the frequency of measurement. Frequency is rather slow here. Here these frequencies are from about kilohertz to few hertz. So it is very low frequency on atomic scale, many orders.
So they're measuring by some lock-in technique?
Yes, yes. Yes,
So do you all know what is a lock-in technique?
You apply AC magnetic field and you measure magnetization at the same frequency.
So that's a trick experiment in this team.
So depending on this frequency, there is a shift of the data. You see, shift is not very large, but sufficiently large to measure it. And systematically, with increase of frequency, the position of this maximum shifts to higher temperature. And also, maximum becomes more rounded. Increase of frequency, in some sense, leads to evolution similar to increase of the amplitude. Here another example of the same frequency dependence. On another material here is dielectric spin glass European stone surface. Here frequency is fixed, but there are just different concentrations of magnetic material. On the second, on the right part of this plot, the data for dielectric susceptibility of dielectric dipole glass. Here, range of measurements of frequency measurements in dielectric glasses is very broad. It is, as you may see here, from 10 Hz to megahertz. And the effect, what is measured is dielectric constant, epsilon. It reaches 10 to 4 at the lowest frequency and around transition point. But you can notice that with increase of frequency, the presence of maximum survive, but the position and temperature and magnitude changes.
Sorry, and here in the dielectric experiment there is no magnetic field.
Of course,
Okay.
here it is instead of magnetic field, it's electric.
Okay, okay.
Another example of extremely slow dynamics now is magnetic dipole system. This is a frequency dependence of real and imaginary part of magnetic susceptibility as function of frequency for different temperatures, from lower 177 up to no, just the opposite. 77 it is the
77 to 350 millikelvin.
millicalorie.
Yes.
So, but what I want to emphasize is that evolution of this, for example, imaginary part, dissipative part of susceptibility, how it looks like in terms of frequencies. It shows extremely broad peak as function of logarithm of frequency. There is no any well-defined time scale. There are many time scales, many orders of magnitude time scales. Now, the question, which was very actively discussed in 80s, what actually we have? Do we have some well-defined phase transition at some temperature? Phase transition into some unusual non-ergodic state, but at some fixed temperature? Or do we have just continuous slowing down? We cool the system, and from some moment we see that on our measurement scale, time scale, frequency scale, there is some kind of freezing. Now let's go to longer time scale. This characteristic temperature changes. Will it separate finally at in the infinite time scale, if we can imagine it? Will it separate to something? This example shows that it seems it is going to separate. Range from 10 to 5 Hz to 0.1, 0.2 Hz. And it seems that this curve curves down and shows to some non-zero temperature. There are some, yeah?
Sorry, once again, on y-axis here it is this freezing temperature.
It is inverse temperature, inverse freezing temperature, yes.
Yes, but freezing temperature itself, it is what?
Is the temperature of the transition. Where
It
you
is
see
where you see apparent something.
Something, yes, exactly, something, you mean,
It's
You
like,
mean this
Like
raw
you
peaks or-
start to see history dependence.
yeah, it's
ah,
like
okay, so the moment when my samples start to show this like magnetization plots, which are different for zero
Yes.
field cooled and field cooled, we call
Yes.
it this like freezing temperature. Okay, thank you.
Yep.
Now, at this point, in the opposite direction.
I'm so sorry, but before we go on too far, so so far you shown like several evidences, very different plots, and are they all connected to the same phenomena, let's say? In the sense that, for example, is this like freezing temperature is the temperature where I stop seeing these broad peaks on previous spot if you go back for one slide? Do I understand correctly that at freezing temperature these like very wide peaks become narrow? Also.
No, rather, you see, some of plots which I show is a function, some susceptibility, a function of frequency,
Yes,
and
yes.
some others are a function of temperature.
Yes.
It is what you need to discuss this question is to fix frequency, to change temperature, and look and find the temperature where difference between two types of quantization measurements appears. You can distinguish between, say, zero field cool density and field cool.
Oh, okay. I'm very sorry. So, wait. Okay, I may ask those questions later.
So, one of very important papers at this period was shown here by Suki. He was here discussing evidences collected to this moment, which shows that at least in some examples of spin glasses, indeed there is a real thermodynamic phase transition. Not just continuous slowing down of the increase, which also is a possibility. Like you have some, you can imagine some big, large but finite clusters of magnetic spins, which needs to overcome large energy barriers to flip, with decreased temperature, so the rate of such transition slows down. But it is not real thermodynamic transitions. So the question is, do we have thermodynamic transition or some continuous slowing down of the increase? Here comes very important point related to, in particular, to this data from Canella and Midas, which I already mentioned. Let us consider even above apparent freezing point, dependence of magnetization, or here magnetization divided by magnetic field, in terms of expansion in h squared. The usual quantity which is measured in ferromagnets, for example, is a susceptibility as a limit of this m over h at low h. But here we need to consider second term, which is proportional to h squared, which is called nonlinear susceptibility. We can also consider the next one, like h to the 4 and multiplied by some other susceptibility. Here, if you have sufficiently detailed measurements of ionization as function of field at different temperature, you can extract from this data this high NL, this is high 3, third derivative of magnetization over magnetic field, and the next one will be high 5, field derivative. What we see here is this plot is a divergence of this nonlinear susceptibility. Then we approach some temperature. If divergence is very serious, it goes to by orders of magnitude. On the left plot, And you see, there is a power law behavior. All that can be extracted from measurements like shown here, if you have sufficiently detailed data. So it seems there is some temperature where these nonlinear susceptibilities really diverge, which is indication for thermodynamic transition. Analysis of this transition was provided in the same way by Sunti, where this is a scaling analysis of magnetization for usual ferromagnet nickel. Magnetization is function of magnetic field and proximity to ferromagnetic transition. So this theta is a T minus Tc over Tc, reduced temperature. And the parameter eta is a ratio of magnetic field to temperature. Oh, of course it should be some Bohr magneton constant there. So this empty circles on the plot shows the behavior of reduced variable. R is defined as a derivative of thermodynamic potential J over effective magnetic field. It should scale as a function of eta and proximity to critical. These open circles corresponds to data for standard ferromagnet nickel. No doubt we have a thermodynamic phase transition. Now, let us try to repeat the same kind of analysis for spin glass. But now we need some modifications. First, because of randomness of the spin glass state, the effective field is not H but H squared. So eta is here H over Tc squared. And the quantity we need to look for is this magnetization divided by H squared. So the major point is that the same kind of analysis now applied to spin glass open magnetized leads to a collection of field circles, which is very similar to the previous one. From this comparison, it seems evident that indeed we have thermodynamic phase transition, although now into some strange state without usual hot current. Here, in this paper, it was an attempt to extract critical exponents from the measurement of magnetization as function of field. So, the main critical exponent in all this study is this gamma, the exponent which shows how fast nonlinear susceptibility diverges when we approach transition temperature. And here, in particular, in this paper, the argentum manganese system was measured. The exponents are close to 2, a little bit different for different concentration. Actually, the fate of this exponent is rather complicated. You will see that many people measured different materials, analyzed in a similar way, and obtained different values of this critical exponent, although in ideal world it should be always the same, it is the same universality class. But the results are somewhat different. Here is a collection of data different spin glasses, measured, reported in different papers. For example, this, let me write it down. Gamma,
Mhm.
3.4, 3.5, 3.3, then 1.5, 2, quite some spectrum. In some cases, the difference comes from a trivial fact that the scaling analysis was used in a too broad range of temperature. Actually, you need to apply it in a sufficiently close to TC, otherwise there is no reason to expect some simple behavior.
These are all metallic spin glasses.
Yes, I think apart from the last one,
Okay.
I think. This one is also a short-range Ising spin glass. Here, the same exponent gamma was found to be 4.
This is data collapse.
Yes. Yes, this is data collapse. Much later paper, 2011. Here it is a long range non-Kittel spin glass with Ising spins. Apparently, nonlinear exponent gamma is close to 1, very surprisingly.
Mm.
Now, let me switch to another kind of experiment. This was a Monte Carlo experiment done at 85 by Andrew Gievsky, who was able to make a special purpose Monte Carlo computer. He studied Ising spin glass with nearest neighbor coupling, of course, for three-dimensional system up to the size of 64 cube.
Mm.
Surprisingly, these results never were overcome. I found a much later paper of 2013 from a big collaboration led by Parisi. They had some supercomputer. They reported studies for the latest 40. 64 in cube, done in 1985, is not unbeaten till now. This guy was really genius. He made a special purpose computer running so fast with at least all time. And he found a well-defined glassy transition temperature and exponent gamma close to 3. I will later show some more details from this Monte Carlo. It's very interesting work.
So, but wait, Misha,
Yes.
from these exponents, I mean, since gamma is changing a lot from 1 to 2 to 3 to 4, I mean, can one identify universality class from this?
It is difficult. It is
Okay.
difficult. You see, you have a lot of data, and some part of them can be interpreted as a well-defined critical exponent. But when some other part of data comes, they show some different exponents.
Mm-hmm.
It is really a problem.
So it was part of the puzzle.
Yes. Relatively Campbell, analyzing a number of data, concluded there is no universality of critical spin glasses. Another paper says there is universality. Well, it is, you see, here we listed the data which are not exactly the same. This is another exponent Z, dynamic critical exponent. So we are not coinciding, but more or less.
But some of them are numerical because Katzgraber is not an
Yes, yes, of course.
experimentalist.
Of course.
Ogielski is
Ah.
also.
Yeah, this, actually, here we discuss
Antonio
numerical
Polkovnikov is not. Is
Here
numerical.
we discuss different examples of numerical
Okay,
about this.
I understand.
Now, another rather unusual feature of spin glasses. Suppose you are above the transition temperature, your dynamics is not hysteretic, ergodic, so normally you expect that the autocorrelation function in time domain decreases exponentially. There is some characteristic relaxation time. But in spin glasses, you may have a region like Tj less than T less than something, with ratio of this T star to freezing temperature of factor 2 or 3. And in all this range, relaxation function, it is not exponential. It decays like stretch exponential. The exponent beta depends on temperature. The same is seen in a real experiment. On the left here, you see neutron spin echo data on copper manganese spin glass. It also shows stretch exponential behavior with exponent about 1/3. The same was demonstrated by Agiyevsky in his Monte Carlo work. This is the relaxation function, and here it is presented in the form that plot of time divided by logarithm of q of t. So if q of t would be simple exponent, then it would be constant. But it is not constant. It has a slope which shows it, from which you can extract value of this stretch exponent b. And extraction of this beta shows the following here. Below about 4.5, exponents start to decrease from 0, and close to freezing, it reaches about 1/3. 1/3 seems to be some magic number in the story. It is, so when you come closer to freezing, exponent beta approaches 1/3, and also, of course, relaxation time, tau itself, grows very strongly to many orders of magnitude. History dependence, which I already mentioned. Here it is shown for magnetic spin glass. The same phenomenon was found for superconducting high-T ceramics here. And here it is, it can be formulated in the following way. You know that normally good old superconductor shows Meissner effect. glass is different. If you apply magnetic field, not very strong, but still something, you cool, you get a state where magnetic field is inside the center. There is no masking effect. But if you try to change magnetic field now, after cooling, this variation of magnetic field will be screened. The magnetic field inside sample will be frozen at the same value when you cross transition temperature. This is again another demonstration of non-analyticity. If you would first put magnetic field to B plus delta B and cool, you will not have any macroscopic magnetization. But if you first cool and then change magnetic field, then you have a response to some diamagnetic currents which try to fix the value of magnetic field at the, like it was in the beginning. Next feature is called aging. I told you about history dependence of the state on the path you choose on the plane magnetic field temperature. But what is even more funny is that even if you fix a path, you can change the state of your system by varying the velocity on how you move along this path. This is demonstrated on this plot. Temperature is a little bit below freezing, T3. And here you see evolution of magnetization as function of time. It is thermomagnetization, so you cool at some field and then you switch off magnetic field. Magnetization starts to relax. We plot a ratio of actual magnetization as function of time divided by field cooled magnetization. So it decreases, and different curves correspond to different waiting time. You cool, then you wait some time and switch off your field. And then you measure magnetization. If you wait 300 seconds, you have this curve. If you wait much longer, then 100 times longer, here, these people would spend quite a lot of time on their experiments. They wait a long 30,000 seconds, then you will get this curve. Its shape is roughly the same, but it is different still. Qualitatively the same, but you see much slower decay. Decay starts, this is all very compact.
So can you collapse all of them into one curve?
Sometimes
Not
Sometimes
always.
it is possible that this collapse is rather not big.
Okay.
I think I'm going to show something like this on one of the following lectures.
Because if I remember correctly, in indium oxide, it comes out, right? This data collapse.
You mean Vadyakhov?
Yeah,
data?
sure.
Here, for spin glasses, it was done mainly by Mikhail.
Okay.
I will show on later lectures. One more example. This is just Mikhail work. Here I show imaginary part of susceptibility at some frequency, very low frequency. 10 to minus 2 gets very low. You measure this dissipative part of susceptibility Insert shows you that system forget what happens at lower temperatures. This part and this first part can be continuously connected. Something happens at lower temperatures, but when you return back to 12 Kelvin, the knowledge about what happens there disappears.
Sorry, what if you make the experiment where you increase the temperature and go from 12 to 14, then go back to 12?
I will show.
Ah,
I will show you this. But roughly speaking, when you go to higher temperature, you erase the memory.
okay, so you lock.
So let me list major problems which were formulated already at the end of pages. Do we have universality? The answer is still unknown. And how to calculate critical exponents? For real three-dimensional spin glasses, there is no answer. There are some attempts. I will talk about some of them, but here to say to put it simply, there is no theory of real spin glasses. Real, I mean, the real short-range interaction, or even hour interaction. So, what is the origin of this non-exponential stretch exponential decay? How to describe what the parameter below this? The answer to this question was found by Parisi for the model of infinite range spin glasses. When interaction does not decay with distance, but only oscillate in some. But what is the relation of this Parisi solution to real spin glasses? It is still debatable. One of the very important questions which was actively discussed in 90s is the following. For in real spin glasses, is the dynamics parallel, like in different pieces of your sample you have some degrees of freedom which switch independently one from another? Or is it hierarchical, like it was, it came out of Parisi replica symmetry breaking scheme, which I also will discuss. It was a quite intensive discussion with one group of physicists presented arguments for hierarchical dynamics in a real system, and another was trying to describe everything by some parallel events. So just really two different schools of thoughts starting to come. I'm close to the end of this lecture. What's about time?
It's okay, I mean, it's a bit earlier than in the program, but go to lunch earlier.
So, here I put a list of some books and reviews. Most of them are old, but not all. There is a rather recent book in everything will be available on the website.
Oh, okay.
And also, I will, for fun, I will formulate a number of problems to each lecture. Because because first lecture is just introductory. The problems are very, in some sense, very simple.
Well, I wouldn't say very simple.
Okay, so that's it for the first
Okay.
lecture. And the second one will be completely different. I will discuss detailed some specific model of spin glass which will provide a technical solution.
Are there any questions? Okay, so if not, the next lecture is this afternoon at